Let's take a bit more of a look at our quadratic function. Our basic quadratic function, the most basic one, y equals x squared. Okay, and we know it is the graph of the quadratic function. And as I mentioned on Friday, that, with the linear function, is the building block of all polynomials. And in fact, every polynomial can be factorized down to be a combination of linear and quadratic factors. But every quadratic can also be made from the basic one, again, via different transformations, a translation, a rotation, a reflection, or combinations of those. How do you recognize a quadratic? If you weren't sure, well, there's our general quadratic. So what are we looking for? Again, each term only has one variable, but this time the power of one of them is 2 and of the other one is 1. So some ideas with quadratics we can play with by using patterns. First one, this idea of completing the square. So all quadratics then could be written like this. We could complete the square on it. Now it might not be monic, so there could be a coefficient out the front there, so A, and it might be plus or minus some constant number. But when it's in that form, we can read off it straight away what the vertex is. So the vertex would be HK. And that's all to do with shifting the curve around on the number plane. A, as we know, measures the concavity. Is it concave up? Is it concave down? So back to our question, same one we did the other day. I'm not going to draw it again. But if I was to approach it this way, how I would get some of this information out. So x squared plus 8x plus 12, I want to complete the square, so I know we're going to have x and then half the coefficient of x, which in this case is 4. But of course when we square 4, we don't get 12, we get 16. So we subtract 4. And so now I can read off that and I know, oh well, the vertex is -4, -4. Okay, so bang, I get that information straight away. The x-intercepts, well, it's in that form now, so I could solve it like this. X plus 4 squared minus 4 equals 0. Move the 4 to the other side. Something squared is 4. Therefore, it's plus or minus 2. I have my 2 x-intercepts. Okay. This question we looked at the other day. Write down the quadratic with roots 2 and 8 and the vertex 5, 3. Well, if the vertex 5, 3, then I know it must be in this form. Some constant outside of x minus 5 squared plus 3. Sub in the point 2, 0. I could have just as easily subbed in 8, 0. And we get the k minus a third, same as we got the other day. And so there's our quadratic. I could leave it like that, or if I expanded it out, I get the same answer we did the other day. So that's one pattern we could look at. And there's another pattern we could look at with the discriminants. Right? Remind you, the discriminant is that piece under the square root sign. So b squared minus 4ac. The vertex, we know the x value is minus b on 2a. The y value turns out to be minus the discriminant on 4a. Our solutions, well, it's just a quadratic formula when you look at it. Minus b plus or minus the square root of the discriminant over 2a. A couple of notes though. If that discriminant is less than 0, well, you can't find the square root of a negative number. Not with real numbers anyway. So that tells us it won't have any x-intercepts. If it was equal to 0, then it's only going to touch the x-axis. Is it right to call it an x-intercept? But anyway, there's one of them. It just touches, because you're going to go plus or minus 0. Well, that means it's not changing. And if it's greater than 0, then you will get 2 x-intercepts. It will cut it twice. So that's other information the discriminant could tell us. Same question again. How would I use this idea? Well, I'll find the discriminant. It's 16. So I know my vertex minus b on a, and then minus the discriminant on 4a. There it is, minus 4, minus 4. Where this is really useful is those questions where it's asked you to find the maximum or the minimum value. And you don't have to find the axis of symmetry to do it. You could just sub in the minus the discriminant on 4a. Bit more about the discriminants. It also can tell us other things about our roots, our zeros. It can tell us whether or not they're rational numbers or irrational numbers. Now, if the discriminant is greater than 0, we know there's going to be 2 answers. We said it's going to cut it twice. So we know there's going to be 2. They're going to be different and they're going to be real because they exist. If it's equal to 0, there are still two roots. Okay, there are still two roots. They just happen to be the same. See, all quadratics have two roots, just sometimes they're the same. So if the discriminant is equal to 0, we do have two real roots. They happen to be the same, which means it touches the x-axis once. And if it's less than 0, there are no real roots. Again, there are still two roots, but they're just not real. They're imaginary. This is when it never cuts the x-axis. If the discriminant is a perfect square, then I know the roots are rational because I can find the square root of that number. I won't be left with an irrational number. So that's something our discriminant can tell us. Let's describe the roots of this equation. We work out the discriminant, it's 60, it's greater than 0. So what are all the different things I know? Okay, there's two of them. They're different, they're real, and they're irrational. All that information from one number, two different real irrational roots. Now they're telling me that this particular equation doesn't have any roots. So what's k? Well, I know it doesn't have any real roots. Another way of saying that is they're unreal. Well, fantastic. I prefer that to imaginary because imaginary sort of implies they don't exist, but unreal just tells you they're really good. But anyway, unreal roots occur when the discriminant is less than 0. So we just have to solve this. And we end up with k is greater than 2. So anytime k is greater than 2 for this equation, we will end up with imaginary or unreal roots. That shall do us for today.